So we can start today's seminar, one word probability seminar. It's a pleasure to have today Zoraida, Rico, and Roberto Oliveira from IMPA, and Zoraida from Bocconi, recently actually starting in Bocconi, Milan. So today's talk is going to have also a special format. You will find out soon. And Zoraida is going to start with the Sub-Gaussian estimation and the details in contamination. And the floor is yours. Maybe let me just say that, okay, for the participants to ask questions at any time, please raise your hand in the chat or raise your hand in the Zoom, and we will unmute you. And please, Zoraida, again, sorry.
Okay, thanks a lot to the organizers for the invitation. It's a pleasure to be part of One Word Probability Seminar. I really value the initiative and the effort to build an open and inclusive space for our community. And thank you all for joining online today. I'm also especially happy to give this talk together with Roberto Oliveira. So let's begin. Today we're going to talk about Sub-Gaussian estimation under heavy tails and contamination for means and covariance matrix. Let me start formulating the problem in the simplest version. So that's on the real line. So estimating the mean of a real random variable is one of the fundamental problems in statistics. So the question we want to address is, given an i.i.d. random variables from an unknown probability distribution P, how can we construct an estimator of its expectation, also unknown? So here an estimator is any measurable function of the sample. And if we want to estimate the mean, there is a natural option, that is the arithmetical mean. And this choice is justified by the law of large numbers, which tell us that the arithmetical mean converge to the true expectation with probability 1, as long as that expectation is well defined. In other words, the arithmetical mean is a consistent estimator of the expectation. If in addition, we assume that both the mean and the variance exist, then we get even more. The central limit theorem gives us an asymptotic distribution of the arithmetical mean. And this implies that as the sample grows, the probability of estimating an error is larger than a quantity of the order in blue, sigma times the square root of log 1 over delta divided by n becomes small. And this quantity in blue, it's called Sub-Gaussian error bound. So we would like to have this kind of bounds, similar bounds, but not in an asymptotic setting. We would like to have this in a non-asymptotic setting. And in modern applications of machine learning and statistics, the community is often interested in guarantees that hold with high probability. These kind of bounds are closely related to the problem of confidence intervals. So what we want is the following. For a given confidence level, say 1 minus delta, what is the smallest error that we can hope to guarantee over all the distributions with a given mean and a variance? In other words, given a statistical task, we would like to identify an estimator that achieves the smallest possible error as a function of the sample size, the variance, and the target confidence level. Here, xn hat, it could be any estimator. And the result I'm going to show you now, due to the Broal, Sub-Gaussian, and Oliveira, explains why we like these Sub-Gaussian guarantees. If we only assume that the mean and the variance exist, which correspond alpha equal to 1, then no estimator can do better than the quantity shown in blue. In fact, for any estimator, there is always some distribution for which its error is at least that large. And that quantity in blue for alpha equal to 1 is exactly the Sub-Gaussian error rate. This also tells us that the family includes distributions with infinite variances, cannot achieve the Sub-Gaussian error bound, right? So how is the performance of the arithmetical mean in finite samples? We know that asymptotical is Gaussian. And Catoni showed in 2010 that the Chebyshev inequality is essentially typed. So if we only assume that the data have finite mean and variance, then there are distributions for which the empirical mean cannot perform better than the Chebyshev rate. So if we have heavy tails, the sample mean can perform quite poorly. Note that when the underlying distribution is well behaved, like Sub-Gaussian, the arithmetical mean actually achieve the Sub-Gaussian error bound. Now, let me compare this bound with the asymptotic one. We do get the right dependence on n, but the dependence on the confidence level delta is not as nice. So we ask if we can do better. A remark for applications is that this dependence on the delta is actually very important. In many statistical and machine learning problems, we are not estimating just a single mean by several means at the same time, and mean estimation appears as a basic subroutine in many settings, like stochastic gradient descent, Monte Carlo methods, reinforcement learning, and many others. And in those situations, the delta dependence from the Chebyshev type of bound, it's an issue. And the answer, if can we do better, is surprisingly, it's yes. Catoni presented the first Sub-Gaussian estimator, assuming a finite variance. And a very natural idea when dealing with heavy tails, it's the trend mean estimator. This is one of the oldest ideas in robust statistics. Then we ask, what about the trend mean? And now I'm going to show you some results on the non-asymptotical performance of this estimator. But let's start with what is the trend mean estimator. So the trend mean estimator is defined as following. We are going to order the sample, and we are going to remove the k largest and the k smallest observations, and then we're going to compute the average of the remaining points. And a few remarks. The idea of the trend means goes back to 2K in the early 60s, where it was first explicitly defined. Uber later connected this estimator to the broader framework of robust statistics. And there is also a long line of asymptotical results in the 70s. For instance, Jekyll showed the asymptotical normality of the trend means. Stigler then sharpened the expressions for the asymptotic variance. Hall later provide more precise approximations, and Leger and Romano extended the results in the 90s. The analysis in these works assume considerably more structural of the underlying distribution. And again, they are asymptotic. So the first result is that we prove that with a well-defined mean, mu, and variance sigma, then for a fixed delta between 0 and 1, and the choose of k of order log 1 over delta, and n greater than c times k, then the trend mean estimator is actually a Sub-Gaussian estimator. And we have this absolute constant, C1 and C2. So a natural question is if we can obtain better constants. And the answer is yes. The next result shows that we can reduce the first constant and improve the second one to a nearly optimal values under certain assumptions. And this is closely related with works by Minsker in 2023 and 2024, where he gives conditions under which variance of the median of mean estimator achieve almost optimal constants. Essentially, the second constant C2 becomes 1 plus something that goes to 0. So let me pause here to recall the idea behind the median of means. We divide the sample into several blocks, and we compute the arithmetical mean in each block. Then we take the median of those block averages. And if we choose the number of blocks carefully of the order log 1 over delta, the median of means estimator becomes Sub-Gaussian, even in the presence of heavy tails. So coming back to our setting, for instance, Minsker's 2023 result achieved this under a variant of assumption. And our result is different in two ways. First, the trend mean estimator is easier to compute. And the second, we obtain explicit finite sample bounds that relate the parameter A, that is there, to the quantities appearing in the mild assumptions, while Minsker provides that only asymptotical conditions for this parameter A that goes to 0.
So sorry, just to understand correctly, so in the previous slides, the parameter, the capital C, maybe can we go back very quickly? Is the just, okay, mu, sigma, and capital C.
Yeah.
Okay, thank you.
Okay. Thank you. So now we ask if it's possible a choice of k independent of delta. This will be very interesting in practice because it will allow us to use the same trend parameter across a whole range of confidence intervals. And this idea goes back to the work of De Broal, Herals, Lugosi, and Oliveira. They introduce what are known as multiple delta estimators, a single estimator, but that work simultaneously for a different values of delta. They also prove that the median of mean estimator has this multiple delta property. So our result is that yes, this also in the work of De Broal and collaborators, they show that any estimator that achieving a Sub-Gaussian bound must depend somehow on delta. Then we will need to make stronger assumptions to obtain a delta independent trend parameter. And this result and this theorem shows that mild higher moment assumptions are enough to achieve this task. Here for delta greater than 4 times exponential minus k asterisk, where this k asterisk depend on n, p, and kappa to p. This kappa to p is the ratio between the p norm and the second norm of the centered variable. And well, so we can compare this result with the Bright and collaborators, of course. And the result is restricted for p equal to 4, the bounded kurtosis assumptions, but applies to a larger set of delta. And up to this point, we have focused on Sub-Gaussian concentration bounds for the tree mean. And these bounds are valuable, but they are known to be a bit dramatic, pessimistic. So a natural question is whether these robust estimators also behave well asymptotically, which will give a more realistic picture of their performance. And this idea appeared in the work by Minsker and Nadaut, sorry for the pronunciation, who showed that the certain robust estimators are asymptotically efficient. We showed that the trend means enjoys the same properties when k is fixed, and more. We proved that the trend mean satisfies a type of Gaussian approximation. And under stronger assumptions, the trend mean is not only nearly asymptotically Gaussian in the center, but remains close to the Gaussian, far into the tails. And this stronger tail behavior turns out to be extremely useful for bleeding confidence intervals. Okay, so let's now consider an even heavier tail setting. So we introduce a notation, this new p, that is the LP norm of the centered random variable x1 minus mu. Nu, the 2, it's a sigma, the standard deviation. Nu1 is the mean absolute deviation. And we do not assume that the distribution of the sample is necessarily has finite variance, but also we are going to make this problem a little bit harder. We allow that the sample to be contaminated in an adversarial way. So what is this? So in this model, there is an adversary that observes the random variables, the data, and change a fraction eta arbitrarily of the points. This is a very aggressive type of contamination. It's stronger to the classical one by Hubert. And this kind of adversarial corruption model has been studied extensively in the recent years in the computer science community, and become especially influential after the work of Diakon-Nicolas, Camas, Kane, Lee, Stewart, and their collaborators around 2017. So let's see what happened with the trend mean with heavier tails and this adversarial contamination. And we showed that another nice property of the trend mean is that it's not only robust for heavy tails, also for heavier tails and adversarial contamination. The trend means doesn't require any prior knowledge of the moments, and still achieve the min-max optimal performance. However, it does need to know the desired confidence level of this 1 minus delta, and this dependence on the delta cannot be avoided. So in this result, let me tell you something about the terms. The first term is the contamination term, and the second one is the random fluctuations, and it turns out that both are min-max optimal up to a constant factor. And we note as well that the contamination term is optimal for Sub-Gaussian distributions. And in one dimension, as far as we know, the tree mean is the only estimator of the mean that achieve these guarantees under such minimal moment assumptions that it's p greater or equal than 1. And even in the presence of the contamination, the work of Minsker and Nadut proved a related result for the median of mean estimator, but their bounds require that the p is in the range between 2 and 3, and the part for the q it's equal to 2 for the fluctuation term. And let me tell you briefly the main techniques. So the key idea behind our result is to view the tree mean as an average of conditionally i.i.d. observations. Let me illustrate this idea. When the underlying distribution has no atoms, if we condition on the two tree mean points, then all the observations that fall between them become i.i.d. from the corresponding conditional distribution, and then we can apply the standard concentration inequalities. And for the Gaussian approximation theorem, we use the self-normalized central limit theorem by Jing, Xiao, and Wang. Apply it into the tree mean sample, the trimmed sample, introduce a ratio whose denominator is random. But because the trim sample is bounded, this denominator concentrates tightly around expectation. And two technical points. The distribution might have atoms, so to recover the conditional i.i.d. structures, we apply a quantile transform xi equal to f minus 1 ue. These are uniform distributions. And the second is that under contamination, the tree mean of the contaminated sample has to be compared to an asymptotically tree mean computed on the clean sample without the contaminations. And some open problems. An interesting open problem is to understand the possibilities and the limitations of adapting the level of contamination eta. And everything I told you relies on a structure that is very on the real line, right? And now we move to much more general setting, metric spaces, and Roberto will now explain how to obtain sub-Gaussians and robust guarantees for the Frechet mean estimator in this broader framework. And thank you.
Thank you, Zoraida, for the nice talk for this part. I would say are there any questions from the audience for this first part of the talk from the audience? If not, let me maybe, so in this previous, in the last result we were mentioning, so there was a condition on K to be greater than eta and plus log delta something. I mean, do you ever care about an optimal K in some sense? We cannot hear you. You're muted. Zoraida, we cannot hear you.
Yeah, I think she can hear us, but so we need to we can't. Yeah, you're muted.
Federico, you can ask her in the menu with panelists. You can ask her to unmute.
Yeah, maybe that's easier. I think
if you click on that
now I'm good. Sorry about that.
Okay. So maybe you answered already, but I couldn't hear. Yeah.
Can you see the slides?
Yes, I can see the slides.
Okay, so in these slides you were asking about the K?
Yeah, the condition on K. I mean, you want to do something uniform in K, but like, is there a way of cutting K in an optimal way to have the best concentration?
Okay, we know by Debray and their collaborators that the K has to depend somehow of delta. And since we have adversarial contamination, we need that this K depends as well on the fraction, on the number of points that has been contaminated, so we can remove it. So that's the reason why this K it's equal to something of the order that depends on the contaminated points and on this log 1 over delta. I don't know if that was the question, but in this scenario will be very interesting to understand if we can have a delta that is, because in applications we usually don't know this fraction of contamination, so it is an open problem to solve if we can find a more adaptative estimator. For a eta, for instance, in an interval.
Okay. I see. Nice. Any question from the audience for the moment? If not, we can maybe go directly to the second part out of 3 of the tools from Roberto.
Thank you.
So may I share my screen?
Please.
Okay. Can you see it already?
Yes. And let me just say that okay, now it's the second part of this afternoon of this seminar series today by Roberto Oliveira from IMPA on the second part, robust Sub-Gaussian mean estimators in metric spaces. And please.
All right. Well, thank you very much to the organizers for the invitation to speak in the seminar along with Zoraida. Thanks also to Katie for all the background work. So as Zoraida mentioned, I'm going to be talking about mean estimators in metric spaces. And this is, this is joint work with Zoraida herself, who's, as mentioned before, is Bocconi, Daniel Bartle, who also recently started a position, but in Singapore, and Gabriel Lugosi, who's been in Barcelona for a long time. So I'm going to be talking about a concept that maybe some of you have never heard of. Of course, we know what the mean of a random variable is, right? It's just an integral or an expectation. We know what a mean of a random vector is. So if you're talking about a d-dimensional vector, you just take the entry-wise mean, and there you have it. When you're talking about means in metric spaces, of course, there's no linear structure, right? You cannot integrate a random variable in a metric space. So we have to find an alternative definition. And to make my life simpler, I'm going to make a second moment assumption. What do I mean by that? I mean that I have a metric space X with a metric D. Well, it's script X, I guess. And then I have a random variable X with values in the space script X. And I mean, maybe I want to say that it's the sigma field is a Borel sigma field, but we're not going to be talking about sigma fields too much. But in any case, the assumption I'm going to make is that the expectation of the square distance to some fixed point in your space is finite. Okay? And of course, I mean, it's a simple exercise using the triangle inequality to check that if this is true for a single point O, then it must be true for all points in the metric space, right? What does the Fréchet mean? Well, Fréchet mean is any minimizer of this function that sometimes people call the Fréchet functional. So for a given C in your metric space, you compute the square distance to your random variable X, and you integrate that. That gives you a number, a function of C. Any minimizer of this function is a Fréchet. Okay, so that's a definition. Let's see what it looks like in the simplest possible cases. So on the real line, assuming you have second moment and you use the standard metric, we have this little exercise in basic probability theory that tells you that, right? So the expectation of X minus C squared is just the variance plus the expectation of X minus C, and you square that, right? So basically, this expectation here measures your distance to the true mean of X. And you can see from the formula that the only C that minimizes the above expression is precisely the usual expectation, the mean of X, right? So at least in the case of the real line, Fréchet means generalize the notion of expectation. Well, they correspond to the notion of expectation, really. If you look at RK, so you go into higher dimensions, there's a similar calculation that you can do, where if you take a random vector X and you compute its distance squared to C, and you integrate that, then you have, again, two terms. One is the distance between expectation of X and C squared, and the other one's a constant, right? It's a trace of the covariance matrix. And again, what you have is that the unique minimizer is the usual entry-wise expectation of the vector, right? Let me mention that this is a specific fact about the Euclidean norm. And that's actually a source of examples somehow. If you change the norms, you use L1 norm or LB norm, whatever, then you're changing the definition of the Fréchet mean, right? Because the definition of the Fréchet mean depends on the distance, so changing the norm changes the distance and may change the Fréchet mean. Now let's go to a slightly more interesting example, which is a circle. So, and on the circle, we're going to use the Zork length metric. So we're just measuring distances by the length of the shortest curve connecting two points, right? And so, of course, if you have a uniform distribution over a small arc of the circle, that's like an interval on the real line, right? So this is isometric to an interval. And therefore, you have existence and uniqueness of the Fréchet mean, and this is exactly what you expect. So if you have uniform over a small arc, it's the midpoint that's going to be a Fréchet mean. But of course, you can easily see that if you have a uniform distribution over the whole of the circle, then any point is a Fréchet mean, right? Because it doesn't matter which point you pick, you have exactly the same value, right? So you see that in this very simple example, already you have non-uniqueness of the Fréchet mean, and that's something that will somehow be in the background of the talk later. Right, so why do people care about Fréchet means, right? So basically, people care about Fréchet means because they care about non-Euclidean data, right? So for instance, in statistics, people study things like directional data, so data coming, say that you have these devices that measure wind directions, and mostly you're worried about a vector in a circle, or maybe in a sphere. Sometimes people, and I mean, and like with standard means, right? So when you compute a standard mean of a data set, it's basically a way of attaching a number to that data set, a summary, as statisticians like to call it, right? It's one number that somehow says something about your data set or about your probability distribution. So it's nice that we have some kind of object like that for data in more general spaces. If you're looking about more concrete applications where the definition really matters a lot, then there are things like regression with non-Euclidean objects, and there are people around Hans-Georg Müller at UC Davis working a lot on that. So if you're trying to compute something like a conditional expectation of y given x, if y is not an Euclidean vector or something like that, then maybe the conditional expectation should be a conditional for Fréchet. And then there are other things, applications in machine learning, where people kind of somehow, that there's either an explicit or implicit Fréchet. I'm not going to get into that too much. But let me talk about the specific source of examples for our talk, right? So as I said, okay, Fréchet means on the real line of the standard metric are just standard expectations. Fréchet means the Euclidean space or the Euclidean norm are again standard expectations. On the circle, maybe it gets a bit more interesting, but here's an example that actually matters a lot, and it's going to be kind of our running example. We're going to come back to it towards the end. And so it's this L2 Wasserstein space. So we're looking here, so the metric space is a set of probability measures with a finite second moment, set of probability measures over RK, the finite second moment. And the definition of the distance between two probability measures is the coupling definition. So yeah, so it's a coupling, of course, is you take a random vector yp of distribution p, you take a random vector yq with distribution q, you compute the expected square distance between yp and yq. But of course, for to get an optimal coupling, you have to minimize, right, this overall possible couplings. So of course, there is always at least one coupling, which is when you take yp and yq independent. But if you're trying to minimize this, you probably want to make them as dependent as possible in some sense, right? And this is a nice distance. People know that this gives you a Polish space, right? A complete separable metric space, has all sorts of nice properties. It has a very geometry that's very well studied by now, but still holds maybe, things to be discovered in the future. And we're going to be coming back to this. And maybe let me mention a few applications specifically of Fréchet means in Wasserstein spaces. So sometimes in this case, people talk about Wasserstein barycenters, right? But it's really the Fréchet mean for this metric space with this distance. So again, you have things like regression tasks where your data, instead of consisting of numbers of vectors, consists of probability distributions. There are also examples where you're doing functional data analysis. So data analysis where your objects are functions. And if you want to talk about, so one kind of canonical example is like you're looking at growth curves, right? You go to a pediatrician with your kids, they show you a growth curve and tell you whether your kid, what's the growth pattern for your kid, right? But of course, kids don't grow at the same rate. So not only you have kind of space deformations, meaning that you have fluctuations kind of vertically around the curve, but you also have fluctuations horizontally, where you're saying that basically this kid is growing a bit faster than kids on the same curve at certain times and growing a bit slower at other times. So when we're looking at these things, it turns out that Wasserstein distances come up, and therefore Wasserstein barycenters are very important. And then there are applications that are more like in computer graphics, but since a picture is worth 1,000 words, I'm going to show you a couple of pictures from a paper. I mean, I should have updated this reference by now. There's a published paper by Herbert Spokojny and Suvorikova. And this is just an example in their paper. They're looking at like confidence intervals for Fréchet means. And so this would be a data set consisting of 4 butterflies. And you want to find somehow an average of these butterflies, right? A mean of these butterflies. And there are 2 ways in which you may go about it. One of them is just take an Euclidean mean. So you think of these images as vectors. So they're kind of grayscale images, right? So for each point on the square, right, you discretize the square. For each point, you have a real number. And you average these real numbers. So you get this thing like that looks like 4 butterflies, really, right? When you use the 2 Wasserstein metric, well, I mean, this is a small data set, but what are you doing, right? So you're thinking of the black points as the distribution of mass over the square. You normalize so that everybody has total mass 1. And then you take a Wasserstein barycenter of these images. And then you get something that maybe looks a bit closer to what you would expect, right? So the average of 4 butterflies is one maybe blurry butterfly, but presumably when you take a larger sample size, you'd see something close to kind of the prototypical butterfly in your data set, right? Okay, and if anybody wants to learn more about this subject of the Wasserstein metric and its statistical applications, there are by now lots of nice works by different people. Well, the third book by Sant'Ambrogio is really about optimal transport and Wasserstein metrics as mathematical objects with lots of applications. The other two are more in this direction of statistics. So, okay, so we're mathematicians, right? I've talked about these Fisher means in general spaces. I've given you lots of examples, well, at least some examples, right? But there are general mathematical problems that you might ask about that, mathematical questions that you might ask about such things. Maybe the first one is existence, right? So we know the Fisher means may not be unique because it is a circle example, but what about existence? Can we prove existence of the general conditions? And there are two results that say more or less the same thing. One is in our paper, the other one is a paper by Arthur Quinn Cafe, and which say that basically you need a Polish metric space. Well, that's a sufficient condition, right? So it's fine to say have a Polish metric space, and then you need some sort of compactness property of the closed balls in the space, but you don't really want to impose compactness in the metric topology. What you need is that there's a weak topology over each closed ball that's somehow related to the metric by this condition, right? That you have lower semi-continuity of the metric with respect to this weak topology, right? And this looks like kind of a fancy definition, but the important thing about it is that it covers basically all the examples that we care about. So if you look at about if X is RK with a standard norm, then of course closed balls are compact in the norm topology, so there's no problem. If you're talking about Banach spaces, then it gets more interesting because closed balls are not compact, but they are compact in the weak topology. If the space is separable and reflexive, so everything works. And also, if Wasserstein spaces over RK, you can prove just, I mean, the weak topology would be the standard weak topology over probability measures, and you can prove that this Wasserstein distance is lower semi-continuous in this topology, so everything works. Okay, but now how do people estimate a Fisher mean from a data set, right? So the standard definition is the sample Fisher mean. So I give you i.i.d copies of a random variable x in a metric space. The true Fisher mean would be the minimizer of an expectation, a distance squared from x to c. You just replace this expectation by a sample average, and then you have the sample Fisher mean. And this, by now, a well-studied object. Maybe there are still things to be proven about it. You see that some of the papers that I mentioned are recent. But there's very nice work from the early 2000s by Bhattacharya and Panantenaru about Fisher means on manifolds. So that case is very well understood. And there's much more recent work where you're moving beyond that setting to more general metric spaces. But the point of this talk, however, is that it's similar to what Zoraida just talked about, right? So there is an estimator that's sort of the canonical estimator that displays the role of the sample mean on the real line, but it's not necessarily the best estimator in terms of finite sample results or in terms of data contamination. So what we want to study is really the finite sample problem of estimating the Fisher mean, potentially on the contaminated data. What's the best that we can do? What is an estimator that achieves that? So before I move on, I should probably ask if there are any questions. I mean, I can't see if there are any raised hands, but please, as I wait for questions, I'm going to drink some water.
Maybe let me just ask, so also in the context, for instance, if we think about stochastic processes, like, I don't know, okay, the easiest is the Brownian motion, then okay, also there you have existence. In this standard example, you can also show uniqueness.
So
a diffusion process, let's say, on a finite interval.
On the diffusion process on a finite interval, I think, yeah, it's kind of a tricky case actually, because it's you're dealing with if you're talking about continuous process, right? You're dealing with a non-reflexive Banach space. So the theory that we work with breaks down, and somehow the geometry is not very nice. But I think that in that case, there are results, I mean, positive and negative results about, but I mean, I don't know off the top of my head, but yeah, there are papers by our collaborator, Daniel Bartel, that dealing with stochastic processes. I mean, he's looking at a slightly different problem, but I think that you can find the literature there. So maybe I'll just,
Okay.
yeah, leave it to that, leave it.
Thank you.
Okay, so now let's formulate a precise problem. I mean, it's basically the same problem that Zoraida formulated, but in a more general setting, right? So I give you an element, random element of a metric space. I give you i.i.d copies of X. I'm going to assume, and then I'm going to give you reasons later to assume this. I'm going to assume that somehow there is a unique for shimming, right? A unique minimizer of this expectation of distance squared from X to C. There's a unique C that minimizes. But that's just to make our life simpler. And later we're going to see conditions that ensure this. And our goal is to design a function, really, in principle, any measurable function that takes in the sample and outputs mu hat n with the property that the probability that the distance between mu hat n and mu is less than r with probability 1 minus delta. But of course, you want to make this r as small as possible, right? So we're trying to find, in some sense, the optimal estimator, or at least a very good estimator of the Fisher mean. As Zoraida mentioned, we care a lot about dependence on the sample size. We also care a lot about dependence on this confidence level, this confidence parameter delta. So these are things that we're going to be looking carefully at. But then there's this adversarial contamination model. I'm afraid they didn't use the same letters, the same symbols as Zoraida. But again, that the epsilon equals eta in her talk. So it's just saying that you have your i.i.d sample, but instead of the estimator working on that sample, you're going to have it work on a contaminated sample. What is a contaminated sample? It's a bunch of random variables, and the only thing you know about them is that at most epsilon times n of them, so at most a fraction epsilon of them are different from your i.i.d sample, right? Otherwise, it could be arbitrary. So it's called adversarial because you should imagine that someone who knows everything about you and the estimator you're using is going to come in and going to try to make your life miserable by picking, sample points and doing something bad to them. And this is just a reminder of things you've just seen in Zoraida's talk. So X and bar is just a sample mean. We're thinking here they're one-dimensional real numbers, so you can just average them, right? The sample average thing. And as Zoraida showed, I mean, the best possible R that you get in terms of delta and n and the standard deviation of the data, it's very different if you look at things asymptotically and non-asymptotically. So asymptotically, you have the central limit theorem that gives us this dependence on log 1 over delta. Non-asymptotically, or square root of log 1 over delta. Non-asymptotically, you have Chebyshev that gives you the sigma divided by square root of delta times n. So it's exponentially worse in delta. And as she also argued, by a result of Catoni, you cannot really do better than this. For a finite sample, you can always find a probability distribution that nearly saturates the bound on your right, the bad bound. But then there's this idea of the trend mean, which is just, again, the same thing that you showed in her talk, right? Where you take your contaminated sample, you order the sample points, you choose a trimming parameter, which in this case I'm calling T. So before taking the sample mean, you just drop the T smallest values and the T largest values from the sample, and now you average, right? So that's all there is to the trend mean. And this, as she showed, achieves very good results. I mean, I think somehow I got the constants wrong here because I got them from another paper that with another former student of IMPA. But anyway, I think I mixed up the constants. But one way of writing the result that Zoraida presented, I mean, it might look different from what she showed, but it's really the same thing, or at least a particular case of it, is that by a suitable choice of T, you get an R that has two terms. So here I'm assuming finite variance. So the first term is a random fluctuations term with this sort of Gaussian or sub-Gaussian behavior. And the second term is a contamination term which depends on the LP norms of X centered around mu. And the higher the LP norm, the bigger the exponent on epsilon, right? So epsilon, you should think of it as a small number. So you want to make P large so the exponent gets larger, and that somehow you have a lower dependence on epsilon. But then you have a prefactor that depends on these LP norms, so there's a trade-off, right? So it's somehow, but the estimator, the estimator achieves this trade-off automatically. Okay, so this is what the trend mean does in 1D. So it turns out there's a way to define kind of a trend mean in a metric space, but it's something different. And I'm going to try to explain this slide. So now our i.i.d sample lives in X. Our contaminated data also lives in X. X is the script X, right? The metric space. Now I'm going to use trend means not immediately to produce the estimator, but really to compare 2 points. So take 2 points A and B in your metric space script X, right? You want to know which one is a better candidate for being the Fresnel, right? So you want to know which one is achieves a smaller value of distance squared from X, expected distance squared from X to C, right? So you're going to set up trend means to compare these 2 points, right? So what I'm going to do is I compute this thing for each sample point. I compute the distance squared from X by to A minus distance squared from X by to B. Well, okay, I'm looking at the contaminated point, so it's really X by epsilon. But anyway, so for each data point, for each contaminated data point, I have this quantity somehow comparing A and B. So I have, since I ranges from 1 to n, I have n such points, and I'm going to compute a trend mean of this quantity for each pair A and B, right? At least, I mean, of course, there are uncountably many points. I'm not really computing them for all points, but let vary me per second. So I'm just saying, okay, for each pair A and B, I have these quantities, distance squared from X to Xi to A minus distance squared Xi to B. I have i's ranging from 1 to n, so I compute the trend mean of this quantity. These are real numbers, so I can, right? So the random variables x's, they're not real numbers, but these distances or differences of distances, they are real numbers. So I can compute a trend. So from this, I'm going to define an estimator that's really kind of a minimax estimator. So I'm going to try to minimize over A the sup over B of this trend mean. So it's really like this. So you look at A, and you're comparing it to each point B, and somehow you give a score to A, which is its kind of worst performance against any other B, right? This is the sup inside the curly brackets. And also for each A, you have a number, you have a function of A, and you're minimizing this function, and that tells you what you're going to take as your estimator of the Fresnel mean. So again, you use the trend mean to compare points A to points B, and now you find the A that does the best against the worst possible B for that, right? That's what you do. So it's complicated, and I mean, you might ask questions like, how can you ever compute this? Well, I mean, there are heuristics, but for the time being, let me just say that under assumptions, this is going to be a measurable function, so a well-defined random variable there, right? So not under this condition that like closed balls are closed in a weak topology of some sense, then you can prove that there is a measurable choice of this thing. And now let me show you what the main result is, except that it's going to come with lots of undefined quantities, which I'm gonna spend the remainder of the talk explaining what these things are. So again, you have to choose a training parameter, and it's going to be proportional to epsilon times n, the number of contaminated points, plus log of 1 over delta, which delta being the desired, right? 1 minus delta is your desired confidence, right? So the desired error probability. So if you do that to this estimator I just showed you, it achieves an R has 3 terms in it, right? And one term is easy to understand. This is Brown term, which is just really the square root of the distance squared between x and mu. This for a random vector would be something like the trace of the covariance matrix. for a random vector in RK. There's a second term which has a maximum eigenvalue of some matrix sigma. And again, you should think of the sigma as a covariance matrix. You see there are weird symbols like log mu of x at the bottom, but we'll get to those quickly. And this is saying that you have this. So the first term is like a square root of trace divided by n. The second term is like a maximum eigenvalue times log 1 over delta divided by n. And then you have a contamination term, which again features some LP norms, which I'm going to try to explain to you. So, but it's easier to see what this means if you look at RK with Euclidean distance. So these three terms are actually, okay, in this case, really sigma is the covariance matrix of your random vectors. The Fréchet mean that you're trying to estimate is usual expectation. And what is this estimator achieving, right? So it, again, has three error terms. So the blue term is, it gives you the worst, okay, lambda max of sigma, right? The largest eigenvalue of the covariance gives you the largest variance over the one-dimensional marginals of your random vector, right? This is like PCA, if you like, or simple exercise probability. Look at all one-dimensional marginals, and you have this thing. So the random fluctuations term comes from this largest variance in any direction, and that's where the 1 over delta shows up, right? The log of 1 over delta shows up. Then you have a contamination term, which is again this trade-off between LP norm. And it's again a one-dimensional term in the sense that this term comes from the worst case LP norms over one-dimensional marginals, right? So both the blue term and the purple term, they're somehow worst case one-dimensional things. And then there's a term, well, of course, they're estimating an object that doesn't live in one dimension, lives in k dimensions. So what sometimes people call the complexity term is the price to pay for estimating all directions at once, loosely speaking. And this has a trace of the covariance matrix. So this is not a one-dimensional term. Think of the covariance matrix as being the identity, right? So you have an isotropic random vector, you have an isotropic random vector. So trace of sigma is a trace of the identity, which is k. So this first term is like square root of k over n. So it depends on the dimension. The other two terms, well, the fluctuations term is log 1 over delta divided by n, square root of that, and that's dimension independent. And the third term is also dimension independent. So somehow the separation between a dimension dependent term that doesn't depend, you have a first term that's dimension dependent and doesn't depend on delta or epsilon. And then you have two other terms that are like one dimensional and dependent. One depends on delta and one depends on epsilon. So that's the optimal shape of results. That's the same thing that we get in a general setting, but we have to explain where all these things are coming from, right? What they really mean. So that's, as I said, it's my main purpose for the remainder of the talk. We're going to need to explain things about curvature in geodesic metric spaces, so lots of fancy words, but we'll get to that. And then from that, though, that's complicated geometrical notions, we're going to move on to describe some sort of convexity properties that we get for this Fréchet functional, right? This function that maps each point x to the expected square distance from, takes each point c to the expected square distance from x to c. And we're going to see that all the geometrical properties that we study somehow correspond to convexity of this functional, or strong convexity, which makes everything possible. So again, maybe I should stop and ask if there are any questions at this point.
Yes, I guess there is a question from the audience. Andrei, I don't know if you want to ask.
I have a question. Do you hear me?
Yes.
Yes.
Yes, I'm sorry, I'm out of the office. So short question is, metric space is a very general term. For which metric spaces exactly does this hold? And you're talking in very low dimension. Does this hold? Can this have any meaning in a general dimension? Thanks a lot.
So I'm really sorry, but I couldn't quite understand what you're trying to say. I mean, the sound got
Yes.
a bit noisy.
Maybe I repeat, I hope you hear me. So you're talking about estimation of Fréchet mean in metric spaces. For which metric spaces exactly does this hold? Metric spaces are of many types
so-
and in which dimensions? Thanks.
So, okay, so we're gonna let me give you a summary, but this is gonna come up in the next few slides, right? So if you're talking about non-positively curved metric spaces, then we can deal with all of them, because those in somehow, so you're talking about negative curvature basically. And so non-positively curved spaces, I mean, those are also called Alexandrov spaces. And we're gonna say what that means later. So, but if you like, you can think of manifolds of non-positive sectional curvature at all points. Then if you have non-negative sectional curvature, then we can also say things. So, and then there's a whole theory of metric spaces with non-negative sectional curvature that are going to describe or at least outline. But if you like, you can think of something like the sphere or any positively curved manifold, except that because we want uniqueness of the Fauché mean, we're going to restrict the support of distributions in that case, right? If you think about a high-dimensional sphere, then if you take uniform over the whole sphere, of course, there are infinitely many Fauché means. Every point is a Fauché mean. So you have to restrict to something like maybe because we want quantitative result other than a half space or something like that. Or half sphere, sorry, right? So spherical thing. But so yeah, but I think we'll all become a bit clearer as I move on. Does that answer your question, or at least partially?
Yes, sure. Thanks. All clear. Thank you.
All right. Okay, so now we're going to talk about geometry in metric spaces, and there are a lot of previous work on this. As I mentioned, Bhattacharya, Patran, Gennaro, they worked on asymptotic ethereal manifolds. Then there are much more recent papers about curved metric spaces, right, where you need to talk about curvature in metric spaces with concentration kinds of results and results and expectations. So this last paper by Leguic, Paris, Golay, and Strom is going to be very important for us. So we're going to use many things that they basically unearthed, and then we're going to basically build on their results to achieve our things. So, okay, so, I mean, it's in an audience of probabilists, it's hard to know how much you know or remember about Riemannian geometry. So I'm going to try to give you a very concise and very incomplete recap of the basics of that subject, right? But I mean, there's a lot more things that I'm not covering that I'm going to cover here today. But okay, I'm talking about a Riemannian manifold, so a manifold where for each point on the tangent space, you have a positive definite metric, which gives you an inner product, all sorts of things that allows you to define a metric in the sense of metric spaces over the whole manifolds, and the metrics given by the length of the shortest curve connecting 2 points, right? So if you like, I mean, we're not too worried about that now, but you should think of a complete Riemannian manifold, where for each 2 points, so where all geodesics can be extended, and for any 2 points, you can find length minimizing geodesics. But okay, as I said, you have tangent spaces, and the fact that your Riemannian manifold gives you an inner product and a norm in each tangent space. And now, if you remember your Riemannian geometry, or if you know something about it, right, there are ways to relate tangent vectors to the manifold, to points on the manifold. So maybe you remember what the exponential map means. So the exponential map is I have a point P, and the exponential map at P takes a tangent vector and maps it to a geodesic, right? A geodesic from P to some other point on the manifold, which has the same length as the tangent vector. Right, the log map is sort of the opposite. It takes a point on the manifold. So if I'm computing the log map at Y, I'm taking Y as a point on the manifold. I find a geodesic connecting P and Y, and I look at tangent vector at P. That's a log map. Okay, so this log map is not uniquely defined because there's this notion of the cut locus where, for instance, so the sphere, right? So if you're trying to connect North Pole and South Pole, there are infinitely many geodesics, so the map's not well defined. However, you can still find a sort of a measurable choice of log map, which is really kind of a measurable choice of inverse for the exponential map, which is going to have this property that's analogous to what I said about the exponential map. which is that if you look at the norm of the tangent vector and the distance between P and Y, they're going to be the same. Okay. So the important property is that we have this thing that maps points on the manifold to tangent vectors and preserves distances somehow, right? The norm of the vector is equal to the distance between P and Y. And then there's all sorts of geometrical notions that ensure that you have uniqueness or you don't have uniqueness, but let's put that to one side and just, we're not doing really differentiable things, we're doing measurable things, so that makes life easier. Okay, but let's look at the Fréchet function over here, right? So you have this geometrical structure. What can you say about the Fréchet function? So it turns out, okay, that you can look at first order optimality, right? So you're saying you have a minimizer of a function of a manifold, right? So what's this function? Is the function mapping each point C on the manifold to the distance squared, to the expected distance squared to a random variable x. So x is now a random point on the manifold. And you can try to compute the gradient of this map. It turns out that the gradient of this map is precisely the expectation of the log mu of x. So basically you're saying I have a random x, I have a fixed mu, and I'm saying, okay, the log mu of x is this random tangent vector pointing towards x. And the result is that the gradient of this function is precisely the expectation log mu of x. Well, if it's the gradient of a function, I'm computing the gradient of the minimizer, the gradient needs to be 0. And now what we're going to see is that under certain conditions, we actually have a strong convexity property of the Fréchet function that is going to be very useful. So here I'm comparing things like distance squared from x to y. Y is just any point on the manifold. Minus distance squared from x to mu, where mu is the Fréchet mean. And we're going to see that under some conditions, you're going to have a lower bound of this that has two terms. One is a quadratically growing term. That's distance from y to mu. And this is basically saying that, the Fréchet function grows quadratically away from mu, right? Which kind of makes sense, right? Because it's saying mu is a minimizer, the gradient is 0 there, so expect it to have some quadratic function. And then you have another term that comes from tangent vectors. And what happens if you take expectations of both sides, so you have the Fréchet function at y minus the Fréchet function at mu, then you have this quadratic term, and then you have a term that has expectation equal to 0 because of first order optimality, right? So this sort of question that I haven't told you anything about where it comes from or how you can prove it, it's going to be enough to imply not only to imply uniqueness of the minimizer, of the uniqueness of the Fréchet mean, but also to give you strong properties, quantitative properties. So, but before I tell you where this condition comes from, let me tell you what it gives us in terms of calculation. So I'm going to show you that this Fréchet mean, so let's say I'm talking now about the sample Fréchet mean, right? The standard estimator of the Fréchet mean. I'm going to argue that whenever, right, the sample Fréchet mean is a complicated object to study because it's a minimizer or something. I don't have an explicit formula for it in general, right? However, if under this sort of convexity condition that I showed here, we're going to see that you can bound the distance between the sample Fréchet mean and mu by something like the norm of an average of random vectors with mean 0, right? i.i.d. random vectors with mean 0. So suddenly you move from something geometrically very complicated to something that in probability you understand very well, right? So averages of i.i.d. things with mean 0. Well, how do you prove something like this? Okay, so suppose you have this condition here, this convexity condition, right? So here I'm thinking, I should have said that, I'm thinking that I'm computing the sample Fréchet mean from an i.i.d. sample that's not contaminated, right? We'll get to contamination later. Okay, so you have this convexity condition. You also have something else. So mu hat n is just, y here should be mu hat n. There's a typo. So I'm just saying that I'm comparing the sample Fréchet mean to the true Fréchet mean. So I would have distance squared from mu hat n to mu. So y equals mu hat n. And minus 2 times log of something. But I also have something that tells me I know that the sample Fréchet mean minimizes an empirical average, right? An empirical quantity. And so I know that the sum of this average of distance squared from x sub I to mu hat n is less than the same average for mu, right? So this is saying that the sample Frisch mean minimizes the sample risk or the sample functional, whereas the true Frisch mean minimizes the expectation corresponding to this. So, okay, how do I put these two things together? So what I just showed in the previous slide translates into this, so that if I take this sum of distance squared from xi to mu hat n minus distance squared to xi to mu, I have something greater than or equal to 0. And that's what people sometimes in learning theory or statistics call the empirical risk minimization principle. One, mu hat n is a minimizer of something, mu is not, so you get this inequality. So I'm gonna, by the above inequality, I can rewrite this in terms of tangent vectors and distances and whatnot. And because of, well, inner products are linear, I can move this average over I inside the inner product, right? Just a simple calculation. But now I can use Cauchy-Schwarz to get a lower bound. So you see that, oh, this, again, there's a typo here. So I'm really sorry about this. I don't know what happened. But this xi minus mu should be log mu of x sub I. And then we have this property that somehow the norm of log mu of mu hat n is the distance between mu hat n and mu. So were it not for the typos, you'd be seeing an inequality that implies the thing that I showed before, which is, let me just go back to it. So if you pretend that x sub I minus mu was log mu of x sub I, you have an inequality now for the distance squared between mu hat n and mu, and this norm of an average of random vectors, and that's going to give you this thing that I showed you, right? This bound distance squared between mu hat n and mu is less than something like the norm squared of an average of random vectors with mean 0. And this is really the approach taken by Le Guic, Paris, Gigolet, and Storm in their paper that I mentioned before. But okay, so I give you this geometrical condition, this strong convexity type condition. When does it hold, right? And now I need to talk about curvature a little bit. So in these pictures, you have, in the middle, you have zero curvature, zero sectional curvature. And on the left, you have positive sectional curvature. And on the right, you have negative sectional curvature. And how do you distinguish between these things, right? So sectional curvature, you can view it. Well, of course, you can view it in terms of properties of a metric tensor, your manifold. But there's a way to describe sectional curvature, which is only about triangles on your manifold. Okay, a triangle with 3 points connected by shortest shortest length geodesics, right? Length minimizer geodesic. And what we're gonna see is that positive curvature or non-negative curvature corresponds to triangles that are somehow wider than in Euclidean space, and non-positive curvature or negative curvature corresponds to triangles that are narrower. So how do we make this precise, right? So, okay, so if you have a triple of points on your manifold, you can look at them along with geodesics and connecting them. And you can, it's a theorem that you can always find a corresponding triple in RK with matching side lengths. It's a simple exercise, right? Just from the triangle inequality, which has to hold for any metric space, in particular for any manifold, you can find this. So now I'm going to try to talk about whether triangles are narrow or wide, and for that I need a concept. So if I'm looking at, so remember I have a triangle in the manifold, right? So if I look at X and Y, I have a geodesic connecting them. And now I pick a lambda and I want to say, I want to find the point that, say that lambda is a half, right? So in that case, I want to find a midpoint between X and Y. If lambda is like 0.3, I want to find a point that's sort of 30% of the way between X and Y. So you have the distance from X to Y, you move 30% along the way. That gives you X lambda Y for lambda equals 0.3. And you can do the same, of course, in Euclidean space, and that's easier because it's just, right, in Euclidean space, things are just, geodesics are straight lines, so you look at convex combinations. So, okay, so you have this, again, x lambda y is a point on the geodesic between x and y. That's kind of a lambda percentage along the way from x to y. So if lambda is 0, you're at x. If lambda is a half, you're halfway through. If lambda is 1, you're at y. And you have different percentages in the middle, right? And, okay, non-positive sectional curvature means the following. And it's, so here I have x, lambda, y, and z. So I have a point on the geodesic triangle on the x, y side, and I'm comparing it to the opposite point, right? To the point on that's not neither x or y. And then I do the same thing in Euclidean space, so it should be a z bar here. And non-positive sectional curvature means that this point, this distance between points on the x, y side to z is always smaller or equal to the distance in Euclidean space. So going back to the picture, it's really, the notation somehow is different because I stole this picture from a paper, but it's really saying that you see the negative curvature case in a narrow triangle, the midpoint on the side opposite to x2 is closer to x2 than the corresponding midpoint in Euclidean space. Right? So that's the kind of thing you're looking at. So that's because that's why I'm saying it's a narrower triangle. And no, that's non-positive sectional curvature, so negative curvature or zero curvature. Non-negative sectional curvature is defined by the opposite inequality. So going back to the picture, you see that you have the Euclidean triangle, you have the corresponding triangle, the sphere, and the midpoint opposite to x2 is farther away from x2 than in the sphere than in the Euclidean space, right? So positive curvature, wide triangles, negative curvature, narrow triangles. Okay, but right. Okay, so that's a definition. That's how you define positive or non-positive or non-negative sectional curvature purely in terms of the metric, right? And it turns out that this definition has very strong consequences for this sort of strong convexity property that we're looking at. So by a theorem by a Carl Theodor Stuhm shows that non-positive sectional curvature is equivalent to the inequality that I'm showing at the bottom, that for all points x, y, and p, if you're measuring the distance from x to y squared or the distance from x to p squared, then you have this lower bound in terms of distance squared from y to p minus 2 times something. That's the kind of inequality that I showed before with a constant equal to 1. So non-positive sectional curvature is exactly what you need if you want that inequality to hold with a constant equal to 1 for all points. Now, if you're in a negative sectional curvature, again, a prime example is the sphere. And of course, you don't have uniqueness of Rashin means of the sphere. You have the geometry somehow, you don't have unique geodesics between each points. So the geometry is somehow more complicated if you want to have strong convexity. So what you need to do is to restrict the support of the distribution in order to get something, okay? And it turns out that the right notion, or at least a notion that Leguic et al. Found, is something related to extendability of geodesics, which, I mean, I don't want to spend too much time completely describing this, but it looks complicated. But let me tell you a little something like this. So what is a bi-extendable geodesic? Suppose I have a geodesic from U to X. It's a length minimizing geodesic, right? Bi-extendability means that I can extend the geodesic in both directions a little bit while still keeping it a geodesic. Okay, how does that look like, right? So again, right, so I want to be able to extend geodesics, length minimizing geodesics, while still keeping them length minimizing geodesics, right? And depending on how much I can extend, I get better and better bounds in this constant kappa mu. And what does that look like in the simplest possible example, which is a circle? So if you take the blue set, so if x and mu belong to the blue set, and you have a geodesic between them, it's a small arc on the circle. It's a length minimizing curve between x and mu. And of course, you can extend it a little bit while still keeping it a length minimizing curve, right? The orange set is not like that because it has antipodal points. So for antipodal points, of course, you have two length minimizing geodesics, right? And even if you have 2 points that are not exactly antipodal, but they're very close, and you try to extend the length minimizing geodesics away from them, then you're going to get into trouble, right? So, okay, think of the antipodal points again, right? You can choose either arc between them as a length minimizing geodesic. But any extension of that arc is not a length minimizing geodesic anymore, right? Because it should have a shorter path on the other side. So this example kind of explains that in positive curvature or non-negative curvature, you might have geodesics that are bi-extendable and geodesics that are not. And we need to somehow restrict the supported distributions to the length minimizing things. And okay. And okay, so everything I've mentioned up to now has been about manifolds, but you've seen that I've been careful enough to only talk about notions that require the metric structure. So you need to have a metric space where geodesics are well defined, and then you have non-positive or non-negative curvature, which is defined in terms of triangles, so it's defined in terms of the metric and geodesics. And I've talked about this extendability or bi-extendability of geodesics that also only requires a metric and length minimizing geodesics. The one thing that I've talked about that is not like that is this tangent structure, right? Tangent spaces and log maps and whatnot. But it turns out that there's a more general classes of metric spaces for which you can define tangent spaces, and you do kind of first order differential calculus. And these are what called the Alexandrov spaces. So they're basically, if you have a metric space where you have length minimizing curves joining any 2 points, where you can say the triangles are either systematically narrower or wider than in Euclidean space or in a space of constant sectional curvature. If you have any such metric space, then you can talk not only about geodesics, about length minimization, but you can talk about tangent spaces and gradients and all sorts of things, right? It's a lot more complicated than on a regular manifold. For instance, I mean, this class of metric spaces can include infinite limit dimensional things. It can include complicated objects, but still you have some sort of first order calculus working. And that's precisely what we need to make. And then basically everything that I told you about sectional curvature, bi-extendability, whatever, still makes sense in these spaces. So you have this inequality maybe on the constraints of the supported distribution. And you have this first order property that the expectation of mu of x is 0. So the tangent space here, oh my God, another typo. So P should be mu. And the tangent space is now a Hilbert space, or actually something bigger than a Hilbert space, but you can still think of it as a Hilbert space somehow. Okay, so just to bring you back to the example that I said was the most important one, where back in a Wasserstein space, so Wasserstein has a metric defined in terms of couplings, and we need to know something about tangent spaces there. And there's this very nice and important theorem by Régnier, which is if you're trying to find the optimal coupling between a measure mu and a measure p, and mu is absolutely continuous with respect to Lebesgue, then the coupling is optimal if and only if it's a deterministic map from the vector distribution y mu and the yp. And this deterministic map is not any map, it's the gradient of a convex function. So if I find a map that's the gradient of the complex function that pushes mu forward to p, it necessarily gives you the optimal coupling, and vice versa. If it's an optimal coupling, it has this form. Okay, so somehow there's a lot of structure here, and the bi-extendability property is this. So you need to restrict the support of your distribution. Right, so okay, what I'm talking about here, I have data that's restricted to a subset X of Wasserstein space, and it's going to have Verschimming mu. And so the set X, it has to be a set where I'm restricting these optimal transport maps, right, these gradients of complex functions. So I'm only considering, I have to fix a mu that's absolutely continuous with respect to Lebesgue, and I need to consider the subset of measures which are push forwards of mu by gradients of convex functions, and these convex functions have to satisfy a restriction, which is that they're uniformly convex and alpha smooth. Well, if V is differentiable, this means that the Hessian of V is lower bounded by B, right? The smallest eigenvalue is at least B at beta at all points, and at most alpha at all points. And not only that, you need to have some sort of condition here. So basically, this is saying that you want convex maps that are not too far from quadratic functions. They can translate as much as you like, but they cannot have much faster growth than a parabola. They cannot have slower growth than a parabola. And these parabolas have to be kind of close to one another. So it's kind of a perturbative result, but it's still kind of non-trivial. Okay. Okay, so let me finally finish. I mean, I'm not sure how much time I have, but I just want to show you what the finished product is. So the way we prove a result is that we impose this sort of abstract structure that we saw we can justify in the case of metric spaces with non-positive curvature or non-negative curvature, and then restrictions on the support of the distribution. So we talk about metrics satisfying this property. So we have this parameter kappa mean that's assumed to be positive. We assume that we have this log map from the metric space, or the manifold, if you like, to a Hilbert space, where, and then you have this metric. I mean, somehow these structures are compatible. We have this norm property that the norm of log mu of x is equal to the distance between mu and x. And we have this first order optimality, which is the expectation of log mu of x is 0. So I'm cheating a little bit here because the tangent space here, as I said, is bigger than the Hilbert space. So that's not worried too much. I mean, it's already complicated enough as it is. So I hope you don't mind me lying to make your life a bit less miserable. But it's, so there's a complicated analytic structure. But again, the important thing is that many important examples like Wasserstein space fit into this framework. And under this framework, this paper by Leguic et al. Proved bounds in terms of how close the sample Fréchet mean is to the true Fréchet mean. So these are bounds in expectation, which take the form shown above. They've also proven concentration bounds, but and then there's another paper by Brunel and Serre where they prove a similar bound. But for these concentration bounds, they need a very strong light tail assumption on the distribution, which is that it's Sub-Gaussian, meaning that the distance between x and mu squared has an exponential moment of finite order, right? So this is saying that distance squared from x to mu is very, very light tail. And from that, they can get bounds. So the expectation result is essentially best possible. Nothing's going to beat that, at least for an uncontaminated sample. But, I mean, because we know it's optimal in Hilbert space, say. But the bounds on the light tails are very far from what you'd like to get, even if you make the nicest possible assumption. So suppose you're in Hilbert space or an RK for some K, and you're just looking at Gaussian data. So the bound that I showed in the previous slide, it translates into something like this, that the distance between mu hat n and mu is less than square root of trace times log 1 over delta divided by n with high probability. But the true bound we'd like to get would, at the very least, even without contamination, right? I'm not talking about contamination here. But the bound we'd like to get would have this something that I alluded to a long time ago, which is somehow the trace and the largest eigenvalue are separated into different terms. So you have the trace term, which may depend on the dimension. So again, if sigma is the identity, this is going to be square root of k over n. And the other term is purely one-dimensional, and that's the term that carries the confidence parameter, right? So, and again, because as Zoraida was saying, we care about high probability results, right? We were thinking the lambda somehow, that the delta is somehow very small. So, and the dimension might be very large. So it's a very good idea to try to keep these two terms separate, to not have a product of them, right? And these previous bounds could not achieve that. Okay, so what's our result now? It's basically, this is the estimator that I showed before, this complicated trim mean construction that we use to compare 2 points, A and B. And now we take the minimax optimal A, where time minimize over A, how it compares about the worst possible B. And this is the theorem that I showed before, but now I can explain all terms, I guess. So kappa min is this constant coming from the strong convexity quantity. Expectation of distance squared from x to mu is a term that, again, is unavoidable in Hilbert space. The other two terms, they are one-dimensional, and they come from log mu of x. Again, so remember, x is our random variable in a metric space. We're in a setting where there's a tangent space at mu. So log mu of x is a tangent vector. So the covariance of this random vector and the moments of this random vector are what matter for the one-dimensional term. So for the random fluctuations term, which is blue, and for the contamination term, which is purple, right? So we have a separation to three terms. The brown term carries some dimensional dependence. The blue term and the purple term are not going to depend on the dimension. Rather, they just depend on one, worst case, one-dimensional things on the tangent space. And just to show you what that looks like in Wasserstein space, I mean, Wasserstein is a very nice example, but it's also a terrible example in some sense because it's very hard to do explicit calculations. However, if you restrict Wasserstein to the set of Gaussian measures, then it's there's what's called the Buret-Wasserstein metric, which is really an explicit expression for the Wasserstein distance between two Gaussians in terms of their means and covariances. Okay, so in that case, it's easy to find examples, and it's easy to find examples where the previous bound are going to be something like square root of ambient dimension times log 1 over delta divided by square root of n, where our bounds have, instead of a product, they have a sum. And that's really a major difference if both k and log 1 over delta are large. So that's what I've been able to achieve. I mean, it's all very complicated, but it's good that at least in some simple example that's not Euclidean space, we could show a significant improvement. And I'm going to skip the proof ideas. I mean, you probably have a headache by now with all this synthetic geometry already. But it's basically the main idea is to use some results. I mean, we use this convexity property, so we reduce everything to the study of trim means of a bunch of random variables. And we want to somehow get a uniform bound of these trim means. So it's a trim means over one-dimensional things on the tangent space, and we need to get bounds on them. And luckily, we have in previous work with another very good former student of IMPA, Luca Gezengi, we had some results about if you have a family of trim means and you need to prove a uniform bound on them, then there's a machinery that takes charge of that. And so let me just say, okay, so what did we do, right? So we had this very abstract class of objects called Fauché means. They're defined on metric spaces. They take concrete forms in Euclidean space or in one dimension. More generally, they're complicated to study. And but nevertheless, they're important. They come up in applications. And we wanted to understand better the problem of how well we can estimate Fauché means for finite samples, potentially under contamination. So what we achieved is that we have an estimator defined in terms of trim means, comparing points A and B and this minimax thing that achieves much stronger bounds than what you can get from the sample mean, achieves much stronger bounds in terms of random fluctuation and contamination. These bounds are better than what was previously known in general, and we know they're optimal in Hilbert space or in RK with the Euclidean norm. Right, so we don't know that they're optimal always, but we suspect that they're optimal in most cases that people care about. And let me just mention that this somehow this convexity framework that it also extends to an interesting setting, which is Banach spaces, where the squared norm is uniformly convex, which is the same as a geometrical property that's called uniform convexity of power type 2. Which means that if I'm in the Banach space, I take two vectors of unit norm and I take their midpoint, right? If x and y are far away, this midpoint has norms strictly smaller than 1 by a certain quantitative amount, right? That has to do with the distance between x and y squared. So these spaces are precisely the Banach spaces where the function norm of x squared is uniformly convex. And because uniform convexity is so important for us, we can deal with them. And the main examples are really L alpha norm, so LP or whatever. I mean, we have P for other uses, so we call exponent alpha. So if you think of Euclidean space with a norm that's L alpha for alpha between 1 and 2, then you have you can use this here. The interesting thing though is that usually, except if alpha is equal to 2, this gives you a different notion of mean than the usual expectation, right? So we get bounds that we can, I mean, sometimes the differential mean equals the standard mean, sometimes it doesn't. And we have some work, I mean, some examples in the paper discussing these things. When the two are equal, do we get good rates or not, or whatever? So now, just to finish with some open problems, I mean, you must have suspected at some point that these estimators that we have, this estimator that we have, is not computationally efficient. I mean, at this point, what I told you, well, there exists a measurable function that corresponds to this estimator. That's reason enough to suspect that the thing we have is not very easy to compute, right? In the paper with Lucas Rezende that I mentioned, we had some related, I mean, kind of particular cases of this result, again, in Hilbert space, whatever, where we can write a heuristic to try to compute this estimator. And it's a nice heuristic, seems to work very well, but we cannot prove that it always finds you a good estimator in polynomial time, say, right? So it's a major open problem for all these constructions to try to find a computationally efficient version. I mean, Zoraida and I have worked with a collaborator, Philip Thompson, where you can prove certain things, but we're far still from what would be the optimal. Yeah, and also with Paco Avelia Medina for covariance matrices, but this is different. But anyway, so computationally efficient is difficult to achieve. It's also hard to achieve statistical efficiency. And again, you should be suspicious that since I'm showing you all these mysterious constants C, that what I mean is that things, okay, you have this mysterious C, so things are optimal in some sense up to order of magnitude. But if you really want, you know, statisticians, I don't know, some practically minded people to use your estimator, they'll care a lot about this value of C and about other hidden constants in the analysis. And we'd like to know how to achieve optimal constants. Unfortunately, I mean, this sort of empirical process theory that you use and all the tools of concentration of measure, they are very inadequate somehow for getting optimal constants. So we did 3 means in 1 dimension. Now we could use much more precise tools and get optimal things and get statistical efficiency. But here we don't know how to do it. I mean, so Lucas Rezende again has some results that could be useful for this, but there are still ingredients that are missing there. And then there's this question that, especially for Wasserstein, is very interesting. So somehow the Wasserstein rates, and let me just show them in the Gaussian case because they're easier to understand. The Wasserstein rates are pretty cool, right? So because even in this sort of previous bounds version, which is not ideal, you can see they're estimating some object that lives in infinite dimensions, right? So probability measures infinitely dimensional objects. And you have an estimation rate that looks like a parametric rate, a finite dimensional rate, right? So which is like 1 over square root of n. I mean, of course, I'm showing this for Gaussians, which are finite dimensional in some sense, but this holds even more broadly. So it's really kind of amazing that you can estimate infinite dimensional objects at a rate that's kind of finite dimensional, right? So if you're looking at statistics, you're doing non-parametric statistics, usually you pay a price for that, which is lower rates of convergence. And here we don't seem to pay a price. However, to not pay this price, we need this, oh, sorry, I'm going the wrong direction. So I should, to not pay this price, we need this strong convexity structure. And in Wasserstein space, that imposes very strong restrictions on the support of the probability distribution. Oops. And it's hard. And I mean, the strong restrictions, I mean, they're nice. We can prove that they're non-trivial, but it's still kind of a perturbative regime where we're looking at transportation maps that are not too far from quadratic maps. And then it's really an important question, especially if you want to understand this problem, this important example better, to understand it. Can you push this analysis? Can you somehow say that under, very far away from the perturbative regime, you still have this 1 over square root n rate? Or is it the case that once you expand the support too much, that maybe everything breaks down and then you're back in a kind of non-parametric range, slower versions. And okay, there are other questions about the Banach space cases. There are a few cases where Fréchet means and standard expectations are equal. And when we compare the bounds in those cases, the bounds for Fréchet means somehow are a bit worse than for the usual mean. So there's something to be understood there as well. Excuse me. So yeah, my coughing is a sign that I have already spoken too much. So I'm gonna finish here and thank you for your attention.
Thank you a lot, Roberto, for the nice talk. Are there any questions from the audience? Andrei, yes, please.
Thanks. Yes. Thanks for the talk. A short question I put in the chat is: you analyze also higher moments, higher than mean, actually second, third, fourth, and higher moments with such analysis. I mean, and then construct also immediately estimations like method moments based on all this.
Yeah, sorry, you said method based on what? Sorry.
Method of moments. So could you analyze also Fréchet variance at the moment or fourth higher moment on Alexandrov space? Thanks.
Okay. Right. So yeah, let me say first a few kind of general things about moments. So going back to the theorem. So right. So we're assuming second moments through and through, right? So and then the question is, what do higher moments give you, right? So let's look at the three terms we have here, and let's pretend for the time being they will work in a Hilbert space or the RK with Euclidean norm, right? So we know that this Brown term is not going to be improved even if you have infinitely many moments, if you're a Gaussian distribution. So for this term, higher moments somehow don't matter. And that's also true for the blue term. It's just, in some sense, yeah, going back to old work by Catoni, I mean, even in one dimension, you can prove that somehow you cannot really beat this Gaussian range, right? These things that the central limit theorem give you for any class of probability distributions that's not too small. Oh, so in that sense, I mean, because we know that for Gaussians, it's really the second moment, it's moments up toward the two that describe the bounds, right? So you stop at second moment, these two terms. I mean, okay, as I said, this is Catoni for one dimension. And then there's a much later paper, I think from 2 years ago by Gilles Depersan and Guillaume Licoué, where they show that in higher dimensions, you always have a term, well, I'm not going to be too precise, but a term like this Brown term, a term that's what people call the complexity term, that might carry dependency of the dimension and stuff, but still it comes from second moments. And so it's not, you're not going to get anything from higher moments, right? Now, moving on to the third term, the purple term, this is where contamination comes in, right? And then somehow AMA can even tell you what sort of the optimal contamination strategy is in RK. Well, it's not quite optimal, but it's optimal up to constant, and it's the optimal. So if you think about data in RK, right? So and you want to contaminate the data so as to make it the hardest for the statistician. Basically, what you're going to do is you find the direction, the one-dimensional direction with the largest LP norm, and you perturb the distribution a little bit in that direction. And that's going to give you the optimal thing. So basically, or you can even think of it as just the truncation in one coordinate, right? So you choose one direction, and that's the thing, right? And it turns out that this nu of p times epsilon raised to 1 minus 1 over p is the largest possible amount that this truncation can change the mean in that direction. So that's just a simple calculation. So to come back to your point, I mean, just these are generic things about moments, right? So just saying in this analysis, moments play a role, but for if you're just talking about, again, complexity and random fluctuations terms, is really second moments and how you never leave the Gaussian world. I mean, you never improve the Gaussian bounds. And the higher moments come in these contamination terms, right? Now, as to your suggestion about the method of moments, I mean, we haven't really thought about it. And partly that's because we decided to look at the most general class of problems where you just have a metric space and you have to define everything in terms of distances. I guess you could also look at moments of distances and things like that, right? But we haven't really thought about it. We decided to adopt this sort of, I mean, in disguise, we're doing something very similar to the sample mean. We're using a kind of sample average to compare how the suitability of different points for being Fréchet functionals, except that because we're doing trig means, we have to do this pairwise comparison thing. So, but yeah, it could be interesting. I mean, I would think that at least without contamination, that somehow moments of order higher than 2 wouldn't matter. But because of this phenomenon, that somehow the Gaussian bounds are unbeatable. But it could be that with higher moments and contamination, that would be useful in some way. But I cannot, I mean, I don't have a very good feel for what it would give you, but it could be interesting.
Thanks. Just one small additional thing. How would likelihood function look in this context? Have you thought about this? It's,
How would what?
Statistics with probability. Likelihood function look in this
the
context.
likelihood. Yeah, so that's a good question. So again, we are doing kind of essentially non-parametric things here because we're in. I mean, our metric space could be anything, right? So, and as you probably know, likelihoods can be tricky, right? So even, I mean, if you like the space in L2, it's very easy to have like in L2 with Gaussians, it's easy to have mutually singular measures and things like that. And so, yeah, I'm not sure. I mean, I'm sure that if you're on manifolds and I think, okay, I don't have a precise recollection, but all the theory on manifolds by Bhattacharya and Parateragru, I think it relies on things that are somehow very classical in statistics, where you show that there's a, you know, there's a local asymptotic normality of the likelihood, no matter what the distribution is, and from that you derive all the properties. If you're moving beyond manifolds, it's not clear to me that there's something general enough to cover these examples that we could do. For sure, if you're talking about specific cases, then sometimes you can use a likelihood. But I don't know that there's a kind of general likelihood-based approach that would cover what we're doing. But it is, I mean, again, right? So much of statistics is also driven by specific examples that we care a lot about. In those cases, perhaps likelihood-based methods would be good or even optimal.
Thanks.
Nice, thank you. Any other questions from the audience? If not, yes. Please, you can unmute yourself. Yes.
Yes, hi. Can you hear me, Roberto?
Yeah.
Yeah, so I couldn't tell with your hypotheses if it covers a really simple example where your tangent space it's not a space, it's like a tangent cone would be if you had, say, like a sort of a star,
Yeah.
a point where you have 3 segments coming out. Is this permitted?
Yes,
under your
so
assumption?
the short answer is yes. So let me try to, okay, that's really getting to the heart of this theory of Alexandrov spaces that I mentioned, right? Okay, let me tell you, try to give you an idea of what's going on there. Okay, so, okay, let me go back. Oh, sorry, I went back, but in the wrong direction, so I have to, let me fix that. I tried to go back, but I moved forward. I don't know what I did. Okay, so let me switch again to presentation mode and once more share my screen. And hopefully now you're able to see what I have. Okay, let me go to, yeah, right. So this is the slide that I want to put on the screen. Can you see it?
Yeah.
Lexicon places, etc. Okay. So, okay, so the first question would be, how do you define a tangent structure on an Alexandrov space, right? And then kind of the answer is complicated, but it boils down to saying that you're looking at geodesics emanating from mu, and then you say that two geodesics are equivalent somehow if they kind of approach mu. I mean, as you're going closer to mu, they approach mu at a superlinear rate, right? So expect that like different geodesics can have different tangent spaces. So if you're looking at distance epsilon, you're gonna have, if the tangent spaces are different, the differences between the two geodesics is gonna be like of the order epsilon. If they're the same, it's gonna be like order epsilon squared or something like that. So those are geodesics that declare equivalent. And now the tangent space is really, as you mentioned, a tangent cone, consisting of equivalence classes of directions multiplied by scalars. And so it's a complicated definition, but it's not it's not that bad in the sense that it's sort of a natural thing once you decide that tangent structure should be about geodesics and how close they are to one another as you approach your point.
Yeah, yeah. In the example I was describing, it's extremely simple where there's just three directions. Like the tangent sphere is 3 points, where
Yeah,
you just
exactly.
have three line segments joining at a point. Is this permitted?
Yeah, yes and no, and I'm gonna explain why. So it's permitted to some extent general theory. And then you switch over to, okay, now we so you need somehow to get a good what is it called? If you want to get a good theory, a theory that's good enough, right? So it's permitted at this very basic level. We can talk about tangent spaces, tangent directions, and everything. So if you want to apply our theorems, the answer is no. And I'm going to give you an indirect answer as to why it's no. Because if you make these curvature assumptions and the sort of assumptions that we're making, then you can prove that this tangent cone contains a Hilbert space. So a nice standard Hilbert space. And this Hilbert space contains log mu of x for almost every x. So if you're looking at a random x, right? So this tangent space, this Hilbert space within the tangent space is going to contain log mu of x for all x.
Okay, so that's not true for what the example I said.
That's not true, exactly.
That'd be only, you could get 2/3 at most.
I mean, this specific class of examples would be R trees, right? So trees where you metric trees, I guess, right? So trees where each, not only the kind of combinatorial trees, but you have these line segments between points, between vertices. And for that example, for that setting, so there's a paper by Victor Emmanuel Brunel and maybe Jordan Serre also, where they basically they killed the whole problem. They studied the sample Fréchet mean to as much as possible, right? So and then they get very precise results. There's this interesting phenomenon that pops up that depending on the setup of the distribution, you can have stickiness. You can have that with high probability sample Fréchet mean is exactly equal to the true Fréchet mean.
Right.
But because it's such a, in some sense, okay, the problem with that space from the point of view of this theory, which I didn't make clear, is that it's a negatively curved space, right? It's, I mean, it's the most convex space you can imagine, right? Triangles are very, very narrow. But on the other hand, it doesn't have a curvature, a lower bound of any kind. So it's too negatively curved. And to make this theory work, you need to have both if you need it, you need to have a curvature lower bound as well of some kind.
Yeah. Okay. Yeah, I was thinking the stickiness seemed like it would help for if you're trying to find.
Yeah, so I mean, it helps, but it seems to require a separate analysis. So sometimes math is like that, right? So you'd think that something helps you, but then it brings in kind of technical difficulty. It doesn't match well with the theory developed for other spaces.
Cool. Thanks.
Yeah, you're welcome.
Thank you. I would suggest, okay, we are getting a bit over time, so maybe let's save a few minutes of break and then we complete with the last part of the talk. What do you think? Okay. And let's thank Roberto again. So we resume, I would say, in 3-4 minutes. Okay. So let's go for the last part of the three talks, again by Zoraida.
Okay. Hi again. Now I'm going to talk about a related problem. This is covariance matrix estimation under the setting of adversarial contamination and heavy tails. So let me start with what is this problem about. Given x1 to xn i.i.d. random vectors in RD with covariance matrix sigma, the task is to estimate sigma. And these problems comes up in several important settings, such as principal component analysis, and least square analysis, and some geometric questions like finding isotropic positions and so on. So the goal is to construct an estimator capital E hat n such that with high probability, it's close to the true covariance in the operator norm. Meaning we want that these quadratic forms, V transpose E hat n V and V transpose sigma V, to be close for every direction V. And again, a natural choice is the sample covariance given by this form. There is a lot of asymptotical results for the sample covariance, like the theorem of Bayin in 93. And the study of the covariance in a non-asymptotical setting began in 1997 by a problem in geometry by Kanat, Lavash, and Simonovitz. And it was by Admachas and their collaborators that they established the first rate of convergence in operator norm for the Gaussian distribution in a non-asymptotical setting. And since then, researchers have worked to relax assumptions on the underlying distribution. The best known result is by Trihomirov in 2018 that achieves the optimal rate of the convergence, assuming only that the four moment exists, so for p greater than 4. Similar to requiring that the variance in the mean estimation case. And there was a growing interest in getting dimension-free guarantees for estimating the covariance matrix. So let's define the effective rank. That is that it's given here. It's the trace of the covariance matrix over the operator norm. So we would like to a bound that depends on the effective rank rather than on the dimension. And the Kolchinsky and Lunici in 2017 proved the optimal high probability bound for the sample covariance matrix in the Gaussian case that depends on the effective rank. A note about their proof is that it's based on a generic chaining and it's specific to the Sub-Gaussian assumption. And this result cannot be recovered by applying matrix concentration inequalities. And this is the Sub-Gaussian error bound that we would like to achieve, but under heavier tails and also in the contamination setting. Another note, Chen Gao and Ren observed that if there exists only one outlier in the whole sample, the statistical performance of the sample covariance matrix can be compromised. So let me introduce our assumption about the distributions. And this is called the LPL2 hypercontractivity condition. And the intuition is that in every direction, the one-dimensional marginals satisfies a moment bound. The higher moments are controlled by the second moment. The quantity kappa P2 measures how heavily the tails can be, and we refer to it as the hypercontractivity constant. This kappa K. So there is a large class of distribution that satisfies this norm equivalence condition, the elliptically symmetric distributions with a finite moment order Q, the Sub-Gaussian distributions, the log concave distributions. Other examples are sub-exponential random vectors with a bounded norm, and the T-student distributions with sufficiently large degree of freedom. And this assumption only requires finitely many moments of the vector x, therefore it allowed for relatively heavy tails. And some results, we have the results by Minsker that works in general matrices, and there is a trade-off that the bounds include some extra logarithm factors. It has some Sub-Gaussian flavor, but it's not Sub-Gaussian. Catoni estimator can achieve optimal performance, but their approach requires previous knowledge of certain parameter of the problem. And there is this estimator by Mendelssohn and Chibotrovsky. They propose an estimator based on the median of means in higher dimensions. They're both include, you can see this logarithm factor, extra log factors, and they come from relying on mean-scarce matrix concentration inequalities. Those inequalities carry such log terms, and they cannot be removed generally. But because we are working with a specific type of matrices, like the covariance one, there is a good reason to believe that we can obtain sharper bounds. So what we like is the bounds that I show you by Kolczynski, but under contamination and just with this L2-LP hypercontractivity condition. And before I show you the main result, I want to tell you that there is this parallel result by Abdallah and Chibotrovsky. The first contribution of their work is a dimension-free version of the Tikhomyrov bond that I showed you at the beginning. And then they improve the version of the mean theorem, which I will show you in the next slide. And I would like to thank them for the helpful discussion on this topic. So our main result, this is a joint work with Roberto. It's that given delta, the probability of error that we allow between 0 and 1, and the sample size and the level of contamination between 0 and 1/2, then we can find an estimator that satisfies the optimal min-max optimal error bounds. Just under the hypercontractivity condition. So let me tell you a few things about the terms. The first term, it has the same form under P = 4 moment. And the second term is the dependence on that comes from the contamination. And for the Gaussian case, it is possible to achieve a slightly improved dependence on eta and this work was by Minassian and Shibotrovsky, but they use a rotational invariance property for the Gaussian distribution that we cannot apply to more generally set up. Okay, so before I tell you about the proofs, the proof of this theorem, I would like to tell you as well that there is a result that in this we have heavier tails, but it's not Sub-Gaussian, and it depends on this Q, and we don't know if this is optimal under weaker assumptions. So let's talk about the proof ideas. So we are going to use a trim estimation estimator for this for the covariance matrix. We are going to prove that it's close to the truncated empirical process with high probability. And then in this truncated empirical process, we're going to use Bayesian techniques to find the bounds. So remember that we want to estimate the quadratic form V, the sigma V uniformly over all the vectors in the unit sphere RD. Is going to be equivalent to estimate sigma. And to construct such an estimator, we look to the trim mean estimator, this E hat KV, which it's the smallest, it's the average of the smallest n minus q directional squared projections. And we minimize the subnorm of the deviation of these trim mean estimators and the symmetric matrix that minimize this norm. And we denote this symmetric matrix as capital E hat K. It's important to notice that this actually exists. And also it is close, it is bounded by this suprema in the deviation of this capital E hat K and the covariance matrix in the operator norm. It's bounded by a trimming process. So what we like to found now is to bound this trimming process. So what are we going to do? It's we're going to use we're going to find a bound for this process via a truncated process. And we're going to show this deterministic result that under counting condition that is telling us that for all the directions, the number of quadratic forms that they are greater than B, it's bounded by a T. And in this condition, when we take K of the order of the number of observations contaminated plus T, then we're going to have that this trim empirical process could be approximated to the truncated empirical process. So what we have now, so at a high level now, we would like to have bounds to control both the counting condition and the truncated empirical process. So we have to analyze the suprema of families of random variables. The most common technique for if we want to analyze these supremas are the chaining methods. So we perform discretizations on the parameter set, and we found strong increments for them. But this is going to depend of the that these increments are close, depends on the structure of the distribution. Instead, what we are going to do is use Bayesian techniques developed by Mac Allister in the 90s, Catoni and Audibert. And what is this telling us? So we want to analyze this process. So instead, we're going to look at a smoothed version. We look at an average version that it has been smoothed by these families of Gaussians. Here we have that the capital gamma B gamma, it's the normal mean with the normal with mean B, and covariance matrix gamma identity for gamma greater than 0. And then here we have to be careful about the definition of these distributions, but the most important thing is that with this process, we have very interesting properties. We can control the suprema of this smoothed process via bounds on the moment generated function at a single point in the origin, plus a price that we have to pay related to the Kalbach-Leiber divergence. And this is what is given here. So the suprema of the smoothed version of the empirical process that we want to bound could be bounded by this log, looking just at one point, and plus this price that we pay. So with this, we achieve a kind of Versen type inequality for a truncated empirical process, smoothed truncated empirical process. And now we have the techniques to control the counting condition and the truncated empirical process. So here observe that for the counting condition, these processes are related. So we have in the left, the one that is not smoothed, but this one, the smoothed one is contained in this one that is not smoothed. And also now the bounding the original process is then a matter of quantify the difference between the smoothed and the unsmoothed process. And for the truncated empirical process, we're going to prove that actually this EB and tilde EB gamma, they are close. And we have bounds for this E tilde gamma B. And then that's it at a high level. So we show that the estimator, it's a good for a range of value scales of the form K0, the number of points the number of contaminated points, the effective rank plus log 1 over delta. But the thing here is that we don't know this effective rank, but we could estimate it. So we need to estimate the trace of the covariance matrix and the norm of the covariance matrix. For the trace of the covariance matrix, we want to estimate positive real random variables. We can use the tree mean estimator. And for the norm, we are going to choose K as a fraction of we're going to use K as a fraction of N. And then we're going to have an estimator for this effective rank. And we can choose our final estimator by choosing E hat start is going to be equal to E hat with this trimming parameter. The open problems in the covariance matrix estimation is the huge problem if we can find a computational efficient algorithm that has these nice properties for the min-max error bounds, and also it's good for the contamination. And also, what about the assumptions? Like if it's possible to have avoid this LPL2 hypercontractivity condition. And yeah, that's it. Thank you very much.
Thank you very much, Zoraida. Thank you for the nice talk. Are there any questions from the audience? Doesn't seem so. Let me, out of curiosity, do you have like also Roberto spoke about computational efficiency for the session in other context. You have like an heuristics also here that of some algorithm that looks like efficient. Zoraida, you hear me?
Yes, but I couldn't understand like
in your last in your last slide.
For the covariance matrix.
Yes, for the covariance matrix. Yes.
Yes, like there are some results if you assume Gaussian that the distributions are Gaussian, but with this L2 LP condition, it's condition. It's we are not. I don't think we're close to find an algorithm that is efficient. But there is a lot of work by Nicholas, Kane, and all they who started to work in robustness in high dimensional.
Okay, thank you. There is a question from Andrei. Please.
Yes, thanks. One short question. It's very interesting. Why exactly are PAC base, probably approximately correct base, appropriate for specifically for this case? Just out of interest. Thanks.
So I'm not sure if I heard correctly, but the question was why this PAC base is
yes, why exactly or thanks.
Okay, so in the counting condition, I don't know. Maybe I can share the slides. So using the Gaussian distribution, unlike the gamma, then it's this pi condition works very well because we have this inclusion here. And also it turns out that these two truncated empirical process, the smooth one and the original one, are close. Since the normal distribution is symmetrical, actually, I believe this suprema over all the directions of the sum of the indicators, counting that the quadratic form is not greater than the quadratic form that are larger are less than a t. It could be bounded by something like 2 times the sum of these smooth versions. So for the PAC base, it's very important how to choose the distribution that you're going to use to smooth the process. And in this case, it adapted very well for the counting condition. And as well, it's more technical, but for the truncated empirical process. I'm not sure if I answered the question.
Yes, sure.
Thank you.
So thank you a lot. Any final question from the audience? If not, let me, okay. we can close it. And let me thanks again Zoraida and Roberto for the nice talks. And we are done for today. Thank you a lot. And we resume in 2 weeks with the seminar. Okay.
Right.
And yeah, thank you a lot. And yes, it was very interesting.
Thank you, Fede. Thanks to everybody for being.
Yes. And yeah, actually, okay, we're a bit over time, but I also had maybe like a question, like let's say out of time, do you also in the general framework of abstract metric spaces, and I mean, you were always speaking about Wasserstein 2 and Wasserstein P is things break down, or you need to. You understand my question?
No, I didn't hear what you're saying. Sorry.
No, I was wondering whether the examples and the efficiency of the bounds you showed us, like Wasserstein 2, that were very useful. Wasserstein P, I mean, also the notion of barycenter is a bit more implicit.
Yeah, so
when P is different from 2, so.
Yeah, we don't have any results on that, and that's because somehow I mean, as far as I know, I don't think that the structure. Okay, so the whole notion of tangent spaces and everything becomes more complicated when you take P not equal to 2. And so, in fact, for instance, the tangent space now is something like a Banach space, and then you have a dual, and things become harder to state even, right? So we didn't move in that direction, though we do have things about Banach spaces in the paper, but not Wasserstein. Yeah.
Okay. And then the heuristical
something, but I don't know.
Okay.
Yeah.
And then you were mentioning also these heuristics for this algorithm. It's in a paper of.
Yeah, no, that's in the paper. So we came up with this heuristic in another paper in a different context of really mean estimation in Hilbert space, and kind of that's the paper with Lucas Jesage that just came out in the Annals of Statistics. But the heuristic is kind of simple. So if you're trying to, right, remember that the estimator is a minimum of a maximum, right? So it's a minimum of a soup. And basically you iterate between minimizing in A and maximizing in B. But the thing is that because you have the trimming, right? So you have to kind of change the support somehow, right? So if I give you A and B, you're trimming the mean, so you're keeping some sample points. So now you fix those sample points and you say optimizing B. And now you trim, you have a different trim mean, you have different sample points, so use those points to minimize in A. And you keep doing that, and that seems to work. But I mean, we haven't tested it for Wasserstein or anything like that. But what I can tell you, I talked to a friend who does optimization for a living, and when I told him that we had an alternating minimization method, he was like, "Oh man, those things are so hard to analyze. I mean, can't you come up with a better idea?" That's basically what he said.
Okay, but it seems to work.
Yeah.
Okay. Thank you a lot, and yeah, I let you go as well. I also go.
All right.
And yeah.
Thanks a lot.
Thank you very much.
Thank you very much for the seminar. And okay, with Zoraida, see you at some point.
Yes.
All right.
Ciao.
Ciao.